Hello guys, good morning. Can you guys hear me okay?
Yeah, Suji.
Perfect. Give me 1 minute. I am just looking at a solution real quick. We should be up and running in a minute, guys. Okay, give me 1 second. All right, yeah, so let me share my screen here. So last week, did we do a review of naive-Bayes algorithm? The sort of the theory behind the algorithm. Sorry, I'm asking because I've been teaching a bunch of classes, so I cannot keep straight, where I covered what. So let me show you the materials and let me see if you guys have seen this before.
No, Suji, we need to discuss.
Okay, all right, good. Just wanted to know. So we have the, okay, classification Python is what we are going through. Okay, good. All right, so let's do a quick theory. And then we will do a lab review as well, as usual. Good, guys. So let me quickly go here, Bayes. Right. And let me get the chat window up here, 1 second. And that's it. All right, guys, so let's look at Bayes. So look at our algorithm summary. We did logistic, we did SVM, we're going to do Bayes, right? Now, so the reason it's called Bayes is it makes some assumptions that really don't hold in the real world. So Bayes is a probability-based algorithm. It basically calculates the probability of, for example, what are the chances of, one object being A or B, right? So that's kind of the idea. So it makes two strong assumptions. One, inputs are independent. So meaning all the inputs, inputs don't have, much correlation, right? That's a big assumption. And also it says inputs are equally important. Another big assumption, right? And we know, that's not true. Remember the house price data, right? There are some attributes just for not contributing much. So, but here's the thing, right? Even though it makes these assumptions, it is still effective even when these assumptions don't hold. And that's why we still use it, right? Especially when you have like text data, categorical data, naive Bayes will do really well. So let me give you a quick example. So naive Bayes has a bunch of different implementation, right? Usually, we use multinomial because that's what works best on the categorical data, right? Yeah. So let me do an example here. So here's my input: weather, car, right? So whether sunny, rainy, car working or not working. So these are my inputs. Now, are these inputs independent? Meaning, are they related to each other or they are not related to each other? What do you guys think? Right, go ahead and type in the chat window, please. Yeah. What do you guys think? Are they related? What do you guys think? Yeah, I'd probably say they're not all that related, right? Because, whether your car working or not probably doesn't depend whether it's going to rain or not, right? At least, let's assume it's a good car, right? So we can say, yeah, they are probably not related, right? Yeah, I guess so. So how about this one, right? Here's an input. We are trying to, these are my inputs, right? Basically, we're trying to find, height, weight, foot size. And based on this, we are trying to predict if this person is male or female. Now, don't read too much into this, right? It's just an example. So if these are the inputs, what do you guys think? Are they kind of related? Would you guys say these inputs could be correlated? What do you think? So here you can make a case. Yeah, maybe there's some dependency, right? Probably you can say a person who's taller may have, may weigh more, right? Have a larger, foot size, right? Maybe, right? So maybe you can say maybe there's some relation here and here, right? So you guys get the idea, right? So when you look at the data, you need to figure out how independent they are, right? So how can you guys tell though, right? You can actually say things like, one way we know is correlation matrix. Remember, you guys have done correlation matrix. You can use that. Okay, so let's go through an example of naive Bayes, and it'll make sense. So the same example I'm going to use, the weather and car example. So weather, sunny, car working, right? So I'm going to encode them into ones and zeros. So whether the sunny is 1, rainy is 0, car working 1, not broken is 0, and whether I went out or stayed home, right? So that's going out is 1, stayed home is 0. So if we sort of look at this, I kind of went out 5 times and stayed home 5 times. These are my observations. So the probability theorem says, right? So basic theory of probability theorem says if the events are independent, you can calculate the combined probability by multiplying them. Okay, what does it mean, right? So example is, so let's say I'm doing a coin toss. So what are the chances of me getting a heads in coin toss? 50%, right? Half. Let's say at the same time I'm throwing a dice. What are the chances of getting a 6 on the dice throw? 1/6. Now, are these independent? A coin toss and the dice throw? Or do they depend on each other? No, right? They're independent events, right? So now, so what are the chances of me getting a heads and getting a 6 on the dice throw? Since they're independent event, we can multiply the probability. Does that make sense, guys? Right? So that's the idea behind this theorem. We calculate individual probabilities, and then we calculate the combined probabilities. Yeah? Make sense? So that's why it's called a probability-based theorem, right? So, and we're going to look at something called, so the way you think about this is, right? Chance of B, so the way to read this is probability of A happening given, given B, right? So if B is happening, what are the chances of A happening, right? And then, and that's what the probability theorem follows here, right? And how do you calculate A and B? Basically, if the A and B are independent, you can simply multiply the individual probabilities, right? That's the idea. Okay, so the probability theorem says chance of A happening given B happening is this. Probability of A and B happening divided by probability of B, right? Makes sense. We think about this, right? So this is the basic theorem. Again, we don't need to go too deep into the probability theorem, but basic ideas, right? If you understand this, you understand naive Bayes. So the way to read this is like, what are the chances of A happening given B happening? right? So and then the equation is like, chance of A and B happening at the same time divided by chance of B happening, right? So again, how do you calculate this? And that's where this equation comes in. You can say, if A and B are independent, remember that's the assumption, I can simply multiply the probabilities. So think like the, coin toss and the dice throw, right? That should be example. Okay, so with that, let's actually calculate the probabilities. Now, first probability I'm calculating is, what are the chances of me going out? Remember, this is going out. Going out is 1, staying home is 0, right? So how many times I went out? So what's the probability overall, right? How many times I went out divided by overall number of events, right? So if you plug in the numbers, right? If you go back and count, I went out 5 times, right? Which is 1, 2, 3, 4, 5 out of 10 observations. So basically, by 5 divided by 10, 50%. Equally, the chance of me staying home is also 50%. Why is this important? Because why am I calculating this probability, right? Because in order for me to predict this decision, I need to also understand, whether you like to go out or stay in person, right? Some people are, naturally outdoor people, they like to go out. So your chance of going out increases, right? Because, you are an outdoorsy person. Some people like to stay indoors. So, right, so if I need to predict whether you're going to go out or indoors, I need to know your probability, all right? And that's why this is important, right? So chance of me going out is 50%, 50%. So this is like equal probability, right? So now what we are going to do is we are going to calculate the combination. Okay, weather is sunny, what are the chances of me going out, right? So we know the formula, right? First, we are going to calculate the probability for weather is sunny and I went out divided by, right, weather is sunny. So do the math. And so let's see, let's go back and count. Again, so don't get lost in the numbers, right? Just simple counting game. So look at the ones and ones here. So weather sunny is 1 here, right? Went out is 1. So how many times went out? Weather sunny, we just count 1 and 1 here. 4 times, right? When the weather was sunny, I went out, right? So 4 divided by 5, 80%, right? So now I calculate the probability for, every combination. So for I am sunny, okay, weather is sunny, what are the chances of me going out? If you look at the numbers, numbers will make sense, right? So weather sunny, chance of me going out, I just calculate 80%. Whether it's rainy, chance of me going out. Again, plug in the same formula. So I simply go back and count, right? Whether it's rainy meaning 0, right? So how many times I went out, right? When the weather was 0? Only once, right? So divide this up, right? Only one time I went out when the weather is sunny. So 20%. Right? So we simply calculate all the probabilities, guys. Right? Again, don't get lost in the numbers. It's just simple counting game, right? You count how many times this is 1, how many times this is 1. That's it, right? And so on and so forth. And we calculate all the related probabilities. So this is weather, right? Whether sunny going out, whether sunny staying home, all different combinations. Now I'm doing the same thing for the car. Okay, so I'm saying, okay, car is working. What are the chances of me going out? Okay, so we know how this goes, right? Go back. So car working is, right here, car working is 1. So you count all the ones and where I went out. So if you look at this, 4 out of 5 times I went out. So car was, when I went out 5 times, and out of the 5 times, 4 times the car was working. Right? Plug it in. Calculate the probability, 4 out of 5, right? And then, so you do the same thing, right? So what are the chances, what are the chances of me going out when the car is broken? Again, same thing, go back and count. You'll see only one occurrence I went out when the car is broken. So we calculated the individual probabilities. Yep. So this slide, again, I kind of want you guys to spend some time on your own, kind of looking through the numbers. It'll make sense, right? Simply we are counting when this happened, what are the chances of this happened, right? So, all right, so now that we have individual probabilities, right? So now I have probabilities for weather and car. So what are we going to do? We're going to combine them. So let me show the example here, right? So now the car, sorry, one second. Here, let me look at this one. This is easier. Okay, so here's a question for you, right? Whether a sunny car is working, what are the chances of me going out? Right now we are combining. We already calculated the individual probabilities of, for example, right? When the weather is sunny, what are the chances of me going out? Now I'm combining. Weather is sunny, car is working, right? What are the chances of me going out? Right? So, and here's the formula. Plug into the formula, right? Weather is sunny, car is working, right? 80% divided by multiplied by 0.5, right? 32%. Right? So look through again. If you look at these numbers, we already worked these numbers out, right? Sorry. Okay. And we're simply plugging them in. So whether the sunny car is working, chance of me going out is 32%. Okay. Same thing. Whether the sunny car is working, chance of me staying home. Again, plug in the numbers from the earlier, right? From this table. Sorry, I'm sort of going back and forth, right? Plug in this from this table, and you will get 4%. Yeah. So we have two probabilities. Whether the sunny car is working, I calculate two probabilities. One is for going out, 32%, right? And for staying home is 4%. So the algorithm simply predicts the one with the highest probability. That's it, right? So it says, yeah, I'm going to go out. So what we are doing is, right? So what the algorithm does is like, it creates like a little matrix, right? Like that. So imagine these are my inputs, right? Weather work, car working, and this is the actual decision. And now I'm calculating the probability for going out and staying home. And you can see, right? Again, so it calculates the decision for every single combination. And then it predicts the one with the highest probability, right? So it gets most of them right, but the yellow ones are mispredictions. So you can see here, right? So whether it's rainy, car is broken, right? I mean, by all means, the algorithm says, it's 20% chance you should have stayed home, right? And that's what it predicts, right? I mean, that makes sense too, right? But I went out. Whether a sunny car is working, right? Because the probability, whether going out probability is 32%, staying home is 4%. So the algorithm says, yeah, I should have gone out, but I stayed home. Again, mispredictions, right? These things happen, right? So they're going to make sense, guys, right? Kind of how we do this, right? So simple probability algorithm, calculating the probability for combinations, and then predicting what's available, what's the highest probability. That's it. That's the algorithm. Seems pretty simple, right? And that's why it's called naive, because sometimes the calculations can be very very naive, but in some cases this actually works really well. So that's where you guys are looking at, right? So naive Bayes, right? Kind of when you look at the naive Bayes, the reason we like naive Bayes is it's simple. We just did an example, right? It's very simple, easy to explain, right? It's just a counting algorithm, very fast learner, because right? There's no complex formulas. And like I said, very effective in some real world scenarios. And we will see this when you do all labs, right? It can handle noisy and missing data. Like for example, let's say some of your data is missing, some of it's kind of a little out of range, things like that. Bayes will handle it, right? Also, it only needs a few samples to learn because it's just a counting game, right? And also, since the algorithm is simple, it can scale to large data sets, right? So weaknesses. So, right, it's assumptions. First of all, I'm assuming all are independent. Usually not true. Also assuming all important features. Again, not true, right? But even when these fail, the algorithm still continues to work reasonably well, right? That's why we still use it. So if you have a data set with a lot of numbers, naive Bayes may not work. So for example, right? So remember the house price data, right? So everything is numbers. So when you have data like that, naive Bayes really doesn't really work well. It's really ideal for like text and categorical data. Right? When it's a text like spam data, you guys just did, right? So, and again, like I said, right? So you guys probably use multinomial for your labs. All right. So let's look at the labs, right? So here is the your lab submission. So, right, very good, guys. Thank you. So 12 people submitted. Very good. So what I'm doing is I am sharing the lab solutions here with all the submissions. And today I'm going to look at Sachin's solution. It's pretty good. So let me take a look at this. Right, so a lot of you have submitted. That's very good. Oh, let's go back and look at the where are we? Sorry. Yeah. Right, naive-Bayes. So here's what I want you guys to do. Right, look at the naive-Bayes algorithm. So reading. So naive-Bayes is a pretty simple algorithm. So hopefully you guys had a chance to read this through, and checking the algorithm. Right. So so we looked at what data naive-Bayes really works well. Right, as we say, categorical data or text data. And what are the three types of naive-Bayes, right? You saw, right, Bernoulli and, right, multinomial and Bayesian, I believe. Bayesian, Gaussian, right? Yeah. And so here's a question for you guys. Calculate the probability I get a queen card given the probability I got a face card, right? So kind of like this, right? So imagine a deck. So, right, so you guys know, we know decks pretty well. So we have, right, 52 cards. Right? Okay, so 52 cards. Now, what's the probability of getting a queen? Can you guys tell me? Yeah, let's say without replacement. That's a good question. Yep, very good question. Yeah, so let's say without replacement, meaning like we take it and we don't, right? So what's the chance of getting a queen out of 52 cards? Yep, so, right, 4 queens out of 52 cards. Yep, that's my queen of probability. What's the probability of getting a face card? So when I say face card, basically meaning like, the card with the pictures, right? King, queen, and jack, right? Basically, right? So that's basically, for getting a king, queen, and jack out of 52. What do you guys think? Right? Yeah, so 12, right? Okay. So now here's a question for you guys. So assume I got a face card already. What are the chances it's a queen? There we go, right? So you guys got that, right? So you can assume this already happened. Meaning, yeah, I got a face card already. So like I pull the card out. I say, okay, this is a face card. What do you think is the chance of queen, right? So you get that, right? So now, we have a chance of 4, right? So you just get that, right? 4 divided by 12. So see how this kind of plays out. The numbers, exactly, right? So actually it's 1/3, right? So meaning, so just chance of picking a queen from 52 cards is 4 by 52, right? One of 13, right? The 1 of 13, yeah, I think so, right? And but given I have a face card, that being a queen is pretty high. So you can see how this works, right? So this is what called conditional probabilities, like meaning when one is already given, right? What's the other thing, right? Exactly. So usually these are higher probabilities. Anyway, so just kind of work through an example, makes sense, right? So when you can calculate the individual probabilities, and also given something, you can calculate the other one. Yep. So hopefully that made sense. Very good. So the text is a little messed up. I need to see why the okay, that's fine. But you guys, I hope you guys get the idea, right? Okay. All right, guys. So labs based on this. So now you sort of see, right? Now that we have the algorithms, kind of understand the basics of algorithm, then going and doing classification is, is business as usual, right? We have done a few of those already. So first one I said, okay, make blobs, right? You can either use one of these, right? More or less the same. And then, so I always ask you to do the make blobs first because it'll give you X and Y right away, right? So you don't have to worry about data, data manipulation, you can just use the algorithm. So let me look at the solution, right? So, so here's the make blobs, right? So right, again, 1,000 samples, 2 features, right? 3 centers, right? Exactly, right? So again, now you know this should be pretty familiar to you guys by now. Let me make this a little larger so you can see it, right? Okay, right? The wonderful thing about make blobs is it gives me X and Y right away. And here, you know, so I see Sachin's kind of plotting. So it's kind of pretty cool, right? You sort of see the centers, right, being plotted. Right? So we have remember the 2 features, right? Feature 1 and feature 2. Very good. Okay. So when I demo these things, I really appreciate the attention to detail. Like for example, right, little things. Let me highlight. So you know, like doing labels, like you know, axis label F1 and F2. Sure, I can quickly look at the plot and kind of see, okay, what's being mapped. But when I see, you know, it's nice to see it being just right on the graph, right? So little things, right? And I always encourage you guys to do this, because when somebody is looking at your code, or even when you're looking at the code, like 2 months later, it'll make a big difference, right? So I don't know, again, so you just set the color scheme. So these are little things that make your display nice. So and then we'll put a little title. Yeah. So good work, Sachin. Very good. All right. So this is our data. Okay. And our Y data is basically, remember, these are centers, right? So Y data, we had encode them into numbers. Basically, it's either 0, 1, or 2. That's it, right? So my Y can be 0, 1. So imagine I'm doing like a, let's do our Legos example, right? Kind of like, right? So my input can be one of those, okay, blue's not the right color, right? One of those three classes. There you go, right? So it's a multi-class classification, not just not binary, but my input can be either A, B, or C, right? So very good. So now that I have X and Y, you guys know the drill by now, right? Train, test, split. Now, here's one thing I will tell you guys. Again, this is my personal preference, right? This is about the imports in Python. Some people like to import everything on the top, right? Some people even do like a, so like a separate import blob for all the imports, right? I usually like to do the imports when I use them. Again, it's a personal preference. It's not a best practice or anything, right? So I'll sort of say, let's say I'm using make blobs here. I'll actually do, I'll say, okay, hey, here's my make blobs, right? And here's I'm using pandas, right? Okay, I'm importing pandas. Like I said, just a personal preference, right? I'm just showing it to you guys, so you guys have an option. Because to me, when I look at the notebooks, when I say, okay, hey, okay, there's a plot, I can quickly see this. Again, both are perfectly okay, right? Just giving an option. All right. So, and then train test. So again, here's the thing, right? If I do train test split, so rather than me going up and saying, where's the train test coming in? I would sort of rather, right, have it here. Right? That's it. Again, like I said, this is a personal preference. So there's no fault with Sachin's code. All right, guys, so we do a train test split. So you guys know the drill by now, right? And then here is my Gaussian. So let me do one more thing real quick. So when you do train test, one thing you may want to do is, I don't know if it's below here, actually, yeah. So here, what you want to do is do like a quick printout if you guys like. You can just say, let me see what is, xtrain.shape. And then kind of print out x train shape, right? So this way you can just kind of do like a little sanity check to make sure xtrain, xtest. And then ytrain, ytest. All right, so that's that. Oh, sorry. I should be running along. All right, so there we go, right? So here I sort of see, right, there were like 1,000 samples. And so I'm doing 80-20 splits, 800 for training, 200 for testing. Good, right? So, and also, I like the fact it's the random state. So this way, when we are running the code, you'll get the same split, right? So again, all the practices we used is being put to use, right? So that's very good. All right. And here is the training algorithm, right? So we're initializing Gaussian naive Bayes, right? Again, from this point on, you can see, right? Actually, from this point on, right? Once you figure out X and Y, and this is why I've been sort of pushing you guys to kind of use a template, right? Because once you have X and Y, the rest is pretty much an autopilot, right? And that's a video scikit because the APIs are exactly uniform. You can just copy paste from one notebook to another, and it will just work, right? All right. So, right, neighbor is fit. So fitting on training data, very good, and predicting on the test data. And again, naming conventions are very important. That's very good, right? Again, and that's the thing, right? So when I quickly see this, I was like, oh yeah, I know what this means, right? Because rather than saying ABC, right, naming conventions are very, very important. All right. So, and then calculating the confusion matrix, right? So look at the confusion matrix. So look at that. Okay, so this is interesting, right? So we are getting pretty much accuracy 1. That's intriguing. Okay, accuracy score, Y train, Y product. Okay, yep. Gotcha. Y test, Y product. Okay. Yeah. So we're pretty much getting almost 100% accuracy. Let me see here. Yeah, it should be fairly close. There you go, right? Look at the data. Look at the matrix, the perfect matrix, right? Remember, and also remember, right? The reason it's doing really well is because the data is well separated, right? We look at the graph, right? The data is, they're like, farther apart. There's no overlaps. So it's a very clean data, right? And that's why that's why I recommend you guys use make blobs or these guys, because they will give you pretty clean data to start with. So algorithm scores 100%. Right? You look at the confusion matrix, right? The only diagonals have numbers, everything else is 0. Pretty good, right? All right, so now that we have an idea on, we do the synthetic data, right? We kind of have an idea, okay, so how to do the data, how to do the algorithm, all that. Now let's go to a real world data. This is SMS text data. SMS is in text messages, right? It's a real world data, and you can, right? I gave you guys a notebook to start with because the challenge here was when you have text data, how do you convert text into vectors, right? Meaning how do you extract X and Y from a bunch of text data? So if you look at the data here, right? So let me see. Yeah, there we go, right? So we're reading the data here, and this is what the data is, just 2 columns. First column says if this is a spam or not, spam, ham, right? Same as spam, ham is not spam. And the text message, right? So these are actual text messages, right? And then you can sort of see here, right? I'm guessing this is either from Malaysia or Indonesia. Just kind of, just looking at the sort of the language, right? Yeah. So anyway, so these are like text. Imagine you're getting text messages on your phone, and these days I'm sure you're getting a lot of text messages, right? At least if you're in the US, we're only 1 week from election, so everyone is texting. So my phone is like blowing up, right? Because they'll say, oh, vote yes on this one, vote no on this one, right? There are a lot of text messaging going on. So now the question is, how do you actually classify text as spam or ham, right? So it's a pretty real world case. Now, first thing we have to do, remember, this is what we are trying to predict. So I want to understand how is the data divided. And here we see a pretty lopsided data, right? I have very few spam messages, only 747, but I had a lot more ham messages. Interesting, right? So this may affect our algorithm. We will see, okay? Now, step 3, this is where the challenge for text data is. And usually once you understand one, it's pretty much the same process for all of them, right? So what are we doing here is, so how do I convert text into vectors, right? And this is a challenge, right? So if you look at the data here, let me bring up, that's speech engineering, I think, right? I may have shown you guys this earlier. When you have text data, let me bring this up here. like this, right? It's called converting word into vectors. Imagine a bunch of documents with a bunch of words. Now, how do I represent these words into vectors? So one approach is basically, right, create a matrix. In the rows, we have documents. So in our case, it will be each SMS text will be like, right, each text message will be like in a one row, right? Our columns would be all the unique words we find in the full text, not just that one line in all of my SMS messages, right? So every unique word becomes a column. So as you can imagine, this is going to be a pretty sparse matrix, right? Because if you look at all the text corpus, a simple SMS might have what, 10, 20 words, right? But if you look at all the SMS messages and kind of start, putting, okay, how many messages, how many words I have, there could be thousands of unique words. So you put them all as columns, and then basically what we do is we simply count, right? So for example, I said, okay, document one has one cat, one cow, and one dog, right? So my vector here is, just simply put them up 1, 1, 1. Let's look at document 4, okay? So document 4, I have no cats, 0, right? 2 cows, 2, and 1 dog. So my vector is, 0, 2, 1. You guys sort of see this, right? So this is a very simple way of converting text into vectors. Because remember, machine learning algorithms want numbers, right? They don't deal in words. So we are going to use these, right, for vectors. So that kind of makes sense because the basic algorithm, how are we converting, right? So each sentence, basically what you're doing is, with my lab, yeah, you're kind of counting, okay, unique words, right? And you imagine you're kind of putting like a big matrix, and you could imagine this matrix has maybe thousands of columns, right? Because each unique word becomes a column. And also when you do this matrix, they will also, what they will do is they will lowercase all the text. So for example, all the go will be just one, right? One column. So we don't want two columns for the word go, one uppercase, one lowercase, right? So when we do is text, we convert everything to lowercase, so everything mapped to one column. So can you just kind of visualize that, right? So it'll kind of look like this. So imagine you have a all right. So imagine you have you have message number 1, right? Message 1. So let's say you have, let's just do one, right? So here I'll just do this very simply, right? I have word A, word B, word C, right? Word D, so on and so forth. You guys get the idea, right? So message 1 has only 0 A's, 0 B's, and maybe 2 C's, right? And 2 E's, all right? So my vector is going to be, right, 0, 0, 2, 1, 2. Message 2, right? Let's say that's different words. Like there's one word, sorry, 1A, 0B, right? 1C, 1D. You guys get the idea, right? You're simply counting. And the vector is going to be 1, 0, sorry, let me line them up, 1, 0, 1, 1, 1. That's it. So this is your vector, right? So now if you look at this, each messages are now being converted into a vector. Does that make sense, guys? Yeah. Right. Yep. So now you can imagine, right? So as we're adding more and more columns, this vector is going to get large and large, and most of the columns of the vector are going to be 0, right? Because think about this, right? Because your SMS message is only going to have few words. It's not going to have 10,000 words. Let's say I have 10,000 unique words, right? My SMS out of 10,000 may have 10 words or 20 words. The rest of my columns are 0. So this is what makes this challenging, because this is a very sparse matrix. Does that make sense, guys? Kind of we can visualize there. Okay, so this is basically what's going on. Okay, so how do we do this, right? So basically what we do, right? Then basically inside, so what am I doing is here's my count vectorizer, I'm counting. So the count will give me this individual word counts. But then I'm doing another thing called TF-IDF. This is like scaling, okay? So imagine, right, let me kind of add this here. Let's say I have a word the. Let me move the vector over, right? So as you can imagine, so the is such a common word. Pretty much every text message might have, this the vector. So here, let's say in the first text message, 3 does, right? Second one has 5. I'm just making this up just to make a point. So my vector is now going to be 3 and 5, right? Because the word the happens quite a bit. So pretty much every message has it. But at the same time, this word is not very meaningful, right? If this word happens pretty much in all the messages, this number is going to be pretty high. So this might influence the algorithm. So what TF-IDF does is it looks at the most common words and it kind of shrinks them down, right? Remember the scaling we did the last lab? Right, when you did scaling like age and salary kind of a thing, right? What we did was, doesn't matter what the range was, they all kind of squished down to one particular range, right? So what TF-IDF does, it's sort of I don't want to use the word penalize, it's kind of a strong word, but it basically it sort of shrinks these vectors, right? So instead of 3, TF-IDF will make this into, like, for example, right? And it'll use floating point numbers, right? So this it'll become like 0.001, right? Because the word is not very important. The other one, the 5, might become like 0.00 2 or something, right? So it will basically produce a minimal vector. Because why? Because it notices the word the happens quite a bit overall text. So I'm minimizing it. That's what it is, right? Because if I simulate the count, most common words will have big influence, and that's detrimental. Like if you go to Google and search for the word the, right? I mean, the results are not going to be very meaningful, right? Because that's the most common word. But if you go and search the word for scikit, right, then what you get is meaningful, because scikit is basically a very unique word, right? So you just get that here, right? So most common words are penalized, meaning they're showing down in the vector format. So that's what TF-IDF does. So what I'm doing is I'm doing a pipeline. So how the pipeline works? Very simple, right? So rather than doing this, step by step, right? So kind of like imagine like I'm doing like this, right? So and I see your questions. I'll get to those. So imagine I'm doing like, let's say here's my X, right? So first I'm let's say I'm doing like X1, right? I'm doing a count vectorizer. Actually, let me do this. My X is here, right? So I'm doing a count vectorizer that gives me X1. Then I'm doing TF-IDF, right? That's giving me X2, and this is my final variable, right? So rather than doing this one by one, what we can do is we sort of put these algorithms into a pipeline, right? So this is my count vectorizer, and here's my TF-IDF vectorizer, right? And I feed X into the pipeline, and then out comes X2. But what will happen is scikit will execute each pipeline in sequence. So first stage will execute, it'll take X as input, and its output is X1. And that is basically fed as the input to the next stage. It'll kind of process it, and its output is X2. So your pipeline can be arbitrarily long, right? So you can say, right, you can kind of create like a very long pipeline with multiple steps, and if you feed the input data, right, and out comes output data, let's say X dash, right, with all the transformations applied. Pretty cool, right? So the reason we do it this way is, imagine you have a text transformation scheme. Like for example, you say, all right, when I get text, first thing I'm just making this up, right? First thing I'm cleaning up the text. So you're doing some cleanup, right? Then you are doing like, let's say, lowercase in the letter, right? Because I want everything lowercase. And you're doing something, and you're doing something. And finally, you are doing count vectorizer. And finally, you're doing TF-IDF. So once you have this pipeline set, you can kind of keep reusing them, right? Rather than manually saying, okay, step 1, do this, step 2, do this, step 3, do this, right? What you do is you create a pipeline, and then you simply say, okay, input into the pipeline, everything gets done in sequence, and out comes the process data. Is that going to make sense, guys? Pipeline. Yeah, exactly. Remove stopping words. Thank you. Yeah, exactly. So, there's like things like, removing stop words. There's a lot of things you have to do when you're doing text processing. We are not doing much cleanup here because, the goal here is the algorithm, not the text processing, right? But yeah, whenever you're doing natural language processing, you end up doing tons of cleanup, tons of pre-processing. The cool thing is you can put like a pipeline. And here's another beautiful thing, right? And if you do pipeline, other people can use a pipeline too. Once you publish a pipeline, you can say, hey, it's like a code reuse, right? You're publishing a module, and the module uses a pipeline, and other people can use it too. So everybody has a uniform pre-processing steps, right? So Scikit encourages code reuse. So that's basically what it is, right? So what's my pipeline? I'm doing very simple. I'm first vectorizing counting, right? And then I'm doing TF-IDF, and that's it. So pipeline, see the API, exact same API, fit and transform. So look at the entire data, right? And then transform the data, remember, right? Because why do you need to fit? You will say, if I'm simply counting words, why do you need, fit? Because remember, you need to go first find all the unique words, right? And then put them in alphabet sequence. So you can do this by text, right? Because you need to go and first find, okay, all the words in the entire document, all the documents, and then you sort of sequence them into columns, right? That's why you need to have fit. Remember, fit looks at the entire data, right? And then once you look at the entire data, then you can do transform. So you're sending in the text data, which is the text column, right? Say, here's my input column, and out comes the vector X. And what is the vector? You can see, right? You can see this is a huge matrix of 5500 times 8700. And as we know, it's a sparse matrix, right? Because most of these cells are going to be empty. And that's why it's giving a sparse matrix, because Scikit will store the sparse matrix very efficiently. You don't want to store the matrix like this, right? Because if you store the matrix like this, it's going to be, it's going to be a huge matrix with lots of zeros. It'll be a waste of memory. So there's a very efficient way if you store the sparse matrix, and that's why it is. So it's kind of hard to print this out because, right, you're going to have 8700 columns. How much data do we have? I'm just kind of curious. PD and just do this. Yeah, right. So how many rows? 55, 100 rows, and all those, each row. So you can imagine a matrix with 500 rows, but 8700 columns, right? So, all right, guys, let me take a minute here and then look at some of the questions you guys might have. Right. So first thing is, if you have too many, right? If you have too many columns, then this kind of transformation may not work for you very well, right? You need to find another vectorizer. So the way that you look at the text, right? I have text data. I need to get the vectors. This is just one approach. So I'm simply saying, count all the numbers, and then sort of normalize them using TF-IDF algorithm, right? So TF-IDF is thing like a scaling, right? Remember, when you did the scaling yesterday, you use standard scaler, min-max scaler kind of a thing, right? So very similar to that. And this is a very simple very simple vectorizing algorithm. And you will see this works reasonably well. But in the last few years, we started getting really good word-to-vec algorithms. So for example, if you do something called word-to-vec, right? So this is that, right? So I'll put this link here for you guys, right? So again, what is it doing? It's converting a text data, right? Let me show you guys this example. Right, there you go, right? It's converting a text data. So for example, the word is king. It's converted into a vector that looks like this. There's a bunch of numbers, right? But these numbers actually have meaning. So the way it's encoding the word is very powerful. So you can, and this way I like, so by the way, this is a really amazing blog done by JLMR. I'll put this link for you guys. I'm putting the link here. Yeah. Right, this is pretty good. So again, this algorithm word-to-vec is one algorithm that converts words into vector. Let me show you guys how. We're not going to go into the details, but I'm going to show you guys the basic idea, right? So again, words go in, the algorithm spits out vectors, this is my vector, right? Just a bunch of numbers. Same thing here, right? You can see different numbers. So you can see here, the word king is translated into this many vectors. Just so the whole thing is an array of numbers, right? Array of floating point numbers. Okay. Now, so the cool thing Jay did was he kind of color coded these numbers, right? So take a look at these numbers, right? So king, so the color scheme, like, it was close to 1, it's like red. It was close to negative, like more like blue, right? So if you encode the word king, the colorized vector looks like this. The word man is encoded like this. Again, at the end, remember, at the end of the day, these are just numbers, right? We are simply color coding them just so we can understand the representation, right? So the color coding scheme is like, you go to hardware store, look at a paint, right? Paint's color coding scheme, same thing, right? This is a scheme, right? This is a scale. So, and the woman encoded like this, okay? So you can sort of look at this, right? So, and here's a bunch of text color coding. You can see here, right? And look at the color coding, you can almost pick out some similarities. For example, look at queen and woman, right? You can see their color coding is very similar. You see that, right? Look at woman and girl, even more similar, right? Look at the color codings. Like imagine you're sort of looking at two paint strips side by side, right? And you're sort of comparing the colors. It's pretty remarkable, right? So the word-to-vec algorithm is capturing, not just blindly converting numbers, but if it actually has capturing meaning also, right? So look at boy and man, right? Pretty similar, right? Man and king, right? And water is completely something different, right? Because it has, these are all people. Water is just something else. And if you look at the color coding, it doesn't match very well, right? So one of the cool things in the word-to-vec things like, okay, so here's what happened, right? And this is a famous equation. You will learn this in deep learning. If you take king, the vector for king, subtract the vector for man, right? And add the vector for woman, you get queen. What does it even mean, right? If you look at the color coding scheme, so take a look at this, right? So this is the king vector. Imagine you're sort of subtracting man, right? And adding, so you're remember just vectors, right? Just adding numbers, right? Adding and subtracting numbers. That's it. Nothing fancy. But then you color code them. So look, here's the equation for king minus man plus woman. And this is the vector for, so this is a calculator. Remember, this is a calculator using the vectors, right? And then we color code them. And here's a queen vector. See how similar they are, right? So how do you interpret this? Basically, you said, okay, if the ruler is not a man, but a woman, we call the ruler queen. Pretty cool, huh? So, and this is word-to-vec. So what it means is like, yes, at the end of the day, these are just vectors, right? But they capture meaning, right? So here's another one, right? So, like for example, so and that's why I like Jay's blog really, because one of the cool things he did was because otherwise if we look at the vectors, just numbers. It's very hard to make sense of these numbers, right? Like if we gave a number and said, are these two arrays similar? We cannot, it's very hard to say. So one of the genius ideas he did, he sort of put like a color coding scheme, right? Like a paint strip. And then when you plot them side by side, it's pretty amazing, right? Anyhow, so take a look at this in the blog. So word-to-vec is another encoding scheme that turns words into vectors. And you can see this is already much more powerful than our simple count vector, right? Because count vector is the simplest possible thing. So in the last few years, we have made tremendous progress in converting words into vectors, right? So word-to-vec is one algorithm. I'll put the other one here too, like for example, right? So, all right, this is word-to-vec. You can look at things like BERT, right? GPT, right? These are massive models. What they do is they turn words into vectors, right? Anyway, so it's kind of beyond this one, guys, but it's kind of a very interesting field. We are doing a lot of we are seeing a lot of advancements in converting text into vectors. Anyhow, so back to our point, right? So we need a way to convert our text data into X vector data. And here we just did a simple, count and TF-IDF, right? But like I said, there are much more advanced algorithms out there. The goal is converting words into some notion of vectors, right? That's it. All right. So yeah, so question like if you have a lot of dimensions, maybe you want think about, right? Maybe this may be too sparse matrix. So you need to think about another vectorizing method, right? That can do high dimensional vectors, right? So that's good. Right. So question was from Richard is like, what are the order of words? Absolutely, right? So when the word to vec encodes it considers the word order, and that's why it's able to capture, right, this classic equation. Because if it just randomly encodes the words into into vectors, this wouldn't be true, right? Exactly. So yeah, yeah. So word to vec algorithm does include consider the order of words. Yep. Very good. So question from Gene, I'm kind of looking at and say, if you look at the pattern of the data, interesting. Take a look at BERT, right? That's what I saw. BERT is like a algorithm from Google that actually takes context and the patterns into account. And again, remember, these are very complex and very advanced vectorizers, right? So take a look at this one. It'll give you some ideas, right? BERT conversion. Yep. All right, guys. So let's see. Question was: is there a way to remove most common words in the text? You can, right? So like, for example, remember in this pipeline, my first stage is count vectorizer, right? I could have done something like my pipeline could have done something like, in the pipeline, I could have done something like, first step could be, right, lowercasing everything, right? Remove stop words, right? And then maybe remove, punctuations and things like this, remove numbers and punctuations, right? There's a lot of cleanup you can do. I could have done this, but we're not doing any of that here. Because it's text messages, right? And maybe you want to remove emojis, for example, right? Right, because right, those, right? Anyway, so you guys get the idea, right? There's a lot of things you can do, but here we are not doing any of this. We're just simply vectorizing it. Yeah. Here's the thing: if you're using TF-IDF, you don't need to remove common words because TF-IDF will actually penalize the common words for you. That's a bit right. Like if you have like common words like and, these guys, they after you run them through TF-IDF, they will have very small values and hence very little influence, right? So usually you don't have to worry about common words if you're using TF-IDF, but you can remove it if you like. You can make it part of the right. So maybe like part of the stop words is like you can also like remove also common words. You can do that if you like. All right, let me run through the questions real quickly, guys. Yeah, one column per word because you want to count each occurrence of the word. And that's why your matrix becomes, so for example, right, when the algorithm went through my entire data, so look at the final matrix. So it had 5572 rows. Why? Because my data set has 5572 rows. Okay, so each text message is one row, right? Can you visualize this? But when it went and counted individual words like think, time, going, right, all the stuff, right? It actually found 8,700 unique words. So your matrix is now organized this way. And the order of words matters, right? If you swap A and B in place, the vector will change, right? So yeah, so order is important. So usually what they do is they order like what we call byte ordering, meaning like think of like alphabet ordering, right? So that the alphabet first words come first. Yeah, because you need to have some ordering, otherwise the vector will change. So you can swap the column positions. Makes sense, right? So, all right, guys, good. Great questions, guys. Let me go through here. So the question is, can I plug in other vectorizers? Absolutely, right? So let's say you have a vectorizing method that basically takes, a bunch of text data and give you a vector, which is basically X, by all means, right? I mean, if you're curious, right, you could actually, this is kind of a bonus lab if you can try this out. See if you can plug in word-to-vec vectorizer, right, as part of this. So when you're getting a vector, you're not using the count and TF-IDF, you're plugging in word-to-vec. There should be an algorithm you can write. I don't know if I haven't used the scikit implementation. You should be able to just give text and get a vector back, right? And so you can pretty much plug in any, right, any vectoring algorithms to do this for you guys. Yep. So that's why text is a little tricky because, right, you need to sort of do, because text has context. It's just not like numbers, right? So when you convert text into number vectors, you want to kind of have one algorithm that actually captures the meaning also, not just, just encoding word by word, because then it loses the meaning, right? So that's why Word2Vec, when it came out, it's from Google, by the way, right? When Google announced Word2Vec, it was like a huge revolution. Oh, wow, this is pretty cool, right? Because not only just, vectorizing text, it's also capturing meaning. Okay, good guys, let's move on. All right, so basically we spent some time talking about how to vectorize words, right? Very important factor, but in this TF idea was pretty good. All right, so we did the vector. Also remember we need to factorize Y also, right? Because why? Because Y is right now text data, ham and spam. We cannot use that, right? We need to convert this into a 0, 1 binary data, and right, it's done here too. Right, once you factorize it, right, 0, 1 binary data, good. All right, guys, so now I have my X and I have my Y. That's it, right? So now pretty much it's the same code as you have seen before. This code you could have easily, copy paste it from the previous example. It'll exactly work the same, right? Because once you figure out X and Y. So, right, trying to split, right? Again, you just know the shape, right? Okay, here's my my train data, testing data, initialize naive base, okay, fit, and then predictions. So I like the fact you actually got both training and testing accuracy. That's very good, very important. So let's look at the results, right? Wow, so this is pretty good, right? And so I'm getting about, 96%, 95%, right? So my naive Bayes algorithm is really doing well. You can see here, right? And then the test data, I'm getting 95% accuracy. That's pretty amazing, right? Because, look at this, right? We haven't done any data cleanup, right? And I used a very simple, excuse me, vectorizer, right? And still I'm getting pretty good accuracy. So let's go to the confusion matrix to understand the full story, okay? So looking at the confusion matrix, so we have, binary classification, like 0, 1. What do you guys think? How is it doing on 0? So look at the 0 row. Remember, this is actual, and this is predicted, right? So how do you guys think it's doing on zeros? Doing well, not well? What do you guys think?
Doing well on zeros.
Yeah, it's doing pretty well, right? It's actually doing perfect on zeros, right? So it basically classified all zeros as, into the 0 column. So you can see 0, 0 is what has all the numbers, right? Everything else is 0, right? So that's pretty good. All right, guys, let's look at the 1 row. Like, how is it doing on 1? Remember, this is a binary classification. Like we are doing 0 or 1, right? Kind of, right? Kind of 1 spam, not spam, right? So how's it doing on 1, guys?
It sure seems acceptable. I mean, it's only like 54 and didn't classify it. Yeah, I mean, it would really reduce spam by like 60% or something. Yeah.
Right. So let's look at the 1 row, right? So we expect to see everything under this column in this cell, right? 1, because remember, we want the diagonals to have all the data, right? So I expect to see 1, 1 to have the most of the data, and it does, but also there's quite a bit of data is misclassified as 0, right? Remember, everything in this row is 1, right? So I like to see everything under the 1 column, right? But here it's a bit of a split. So I think, what is it, 2 to 1 maybe, right? So for every 2 it's predicting correctly, it's predicting 1 incorrectly. So about 66% accuracy, right? Like you guys mentioned. So this is kind of revealing, right? So because remember, before I was impressed, I was getting 95% accuracy. And most of the accuracy numbers coming from where? Zeros. 1, it's only exhibiting 66% accuracy. Do you guys see what I'm getting at, right? So question for you guys. So what is 0, what is 1, right? So let's go 0 and 1. 0 is basically, if you look at the matrix, right? Ham is 0, spam is 1, right? That's gonna, I'll just put this one here, right? So, okay, so basically, right? 0 is ham, 1 is spam, right? That's how they'll be encoded. Now, let's say you're putting the algorithm to use, and you send it, you test a text message, and it says this message is good, as in ham. Would you trust the algorithm? If the algorithm says, yeah, this is good, ham. What do you guys think? Think about this for a second and type in the chat window, please. So I sent a test message through this, and this one says, yes, this is a ham meaning good, like not spam, right? Would you trust this model's judgment? What do you guys think? No? Okay, I got some private message saying yes, right? So remember, how good this model's predicting ham? Remember, ham is like not spam, right? So 0. Look at 0 row. Can the model predict 0? Well, yes, right? Because yeah, 0 model is 100% accurate. Can you see this, right? So remember, like spam, my spam is mapped to 1, right? When you do the factorizing, right? Sorry, there we go, right? So I'm mapped to 1, right? And ham is mapped to 0. So when the model predicts 0, it is pretty accurate because right? Because the model can identify 0 pretty effectively. Would you guys say so? Right? So when the model predicts 0, so look at the column-wise, right? Column-wise thing, right? So when the model says 0, most of the time, right, it's actually 0. Only like what, like, what is it, 1,000, 22 1 maybe? Only maybe a 5% chance, right? This is actually 1. So I'm sorry, now looking at the algorithm, the matrix column-wise, right? So remember, right? So can I read this way, guys? Read column-wise, right? So the model says I'm 0. So then look at the 0 split, right? So most of the time, if it says 0, it's correct. It has 956 times it's correct, 54 times it's wrong, right? So if it says model 0, you can see, right? All right, so I should put this one code just so I don't mess up. So it has a, how do you say? Let's say just keep this number simple, right? It says 50 is wrong and 1,000 times is right. So we make it as a percentage, what is it like? Maybe like 5%, right? Just to kind of make it simple, right? So 5% wrong, 95% right. Yeah. Is that gonna make sense, guys, right? So what if the algorithm predicts 1? Yeah, right? So you guys gotta see this, right? See how to interpret the models, right? So look at the confusion matrix. Again, I don't want to go too deep into this, but I want you to think about this, right? So when the algorithm says 1, right, it's basically, right, it's able to do, right, able to predict 1 reasonably okay. Right? So again, again, this is where sort of the metrics will come into play. But so one thing I want to emphasize this is, right, don't look at the accuracy number just by itself and say, aha, this is great, because the most of the accuracy, as you can see, is coming from 0. Now, why do you guys think it's doing well on 0s but not doing well on 1? Because the matrix is kind of, right? 1 is I have perfect classification. Other one is about, only 66% accuracy, right? Why do you guys think that is?
Zeros have more unique words, whereas ones not so many unique words, and sometimes they do.
Exactly. Also, yeah, yep. So look at this one here. You look at the data. Remember, and this is why that this exploration is pretty good, right? I have a lot more 0 data than 1 data. So the algorithm has learned pretty well what makes a zero, what makes a ham, right? But it hasn't had enough data to learn well what spam is, because the data is very lopsided, right? Because I don't have enough spam samples. So that's why. Is that going to make sense, guys? Kind of right? And that's why the data distribution actually affects your algorithm, because algorithm are only as good as what is learning. So here's kind of learning, right? Only partial data. Sorry, partial as in just a tiny fraction. Yeah. Exactly, right? So all these things will matter. I mean, again, if you look at this, right? I mean, this you discover when you are doing exploration, way before even do machine learning. That's why the basic exploration is really good, because it will actually give you an idea of the data, and you can go back and say, okay, what happened, right? I bet if you had enough distribution, like for example, if it's like a 50-50 distribution of ham and spam, this confusion matrix will look pretty clean, right? So it'll, right? So right now, like it's a little, right? It's doing well on one, it's not doing well on the other. Right? The reason is just not enough data. And also, like like you mentioned, it could be the data could be maybe the zero data is very good, one data may not be very good, right? So there can be a multitude of factors. So anyway, so again, the reason I'm spending time on this one, guys, is like, right, kind of you need to be able to understand the algorithm, not just look at one number and kind of look at the confusion matrix and understand what's going on, and also able to reason why this might be happening, right? Okay, right. So great question, Janine. Yeah. So in this case, when you have lopsided data, right, like this, what's that? Yeah, right. Sometimes accuracy may not give you a good measure. So maybe you have to look at recall and sensitivity, right? I'll put a note here for you guys. Can I go back and read? Remember, right? Maybe recall, right? Sensitivity. Look at these metrics. Sensitivity. All right, right. Remember the confusion matrix when you look at the where was that? So classifications, right? So look at confusion matrix, right? Matrix guide and all this stuff, right? Can read this, and also here's another one, right? Evaluation matrix for imbalanced data, and this is exactly the scenario, right? Because we have imbalanced data, right? So read these, right? It'll give you some ideas, right? So which matrix you are considering. But the good news is you already have a confusion matrix, right? Now you can calculate all the other metrics. You did the hard work. Now it's just a matter of picking the metrics and kind of evaluating them. Yeah, that's it. Good, guys. All right. So question is like, what if we, if we just, completely get rid of ham class and, train by, right? Can it do the training? So that's the thought, because, we have a lot of ham data. What's that? Right? Yeah. What if I completely remove ham data? Because that'll be counterproductive, because remember, I want my algorithm to see both data, right? Imagine kind of, right? Imagine kind of, I'm kind of, training the data, and I want to show you guys both. So the algorithm has learned what makes a spam, what makes a ham. But if you only show one data, right? Algorithm, that's not enough, right? Yeah. So what you want to do maybe is, right, you can maybe show balanced data. So for example, you can remove, so since we have a lot of ham data, maybe, you can sort of throw away some ham data and only make them balanced. So maybe your test case will have 50% ham and 50% spam. That you can do. And that's called sampling, right? You can sample less ham data and also make sure the sampling you're doing is equal size. So there are a lot of techniques you can use to kind of, right, and try them out and see how the algorithm. But now here's what's going to happen, right? When you minimize ham data, you're going to lose accuracy on ham, right? So that means this nice confusion matrix row you have here right now, have everything 0. Now you're going to lose some accuracy here. Now it's going to misclassify some zeros as ones, right? So there's no like a free lunch, because when you turn one knob, it's going to affect in the other knob. Kind of like flying, right? You can just like do one correction. You have to do like, because one move will affect the entire equilibrium, right? So if you reduce ham, you probably won't have this, this perfect classification up on the up top. It's going to have some misclassifications. Anyway, right? But again, the beauty of this is you can try this out. So what you can do is you can take the data, you can sample the data and say, I'm going to have 50% ham and 50% spam, and run the algorithm and see what you get for confusion matrix, and then you will see the numbers will be mixed. So yeah, right. So there are a lot of things we can do here, but so I kind of want you to set up with a basic approach, right? So great questions. All right, guys. Finally, right, we are testing some with our own data, and I just added this data right here. So we are testing with our own data, right? Here's my text. So what we are doing is, right, now that my algorithm is trained, let's see, if we can just do our own, right? I took this from Richard's Richard Hughes notebook. Sorry. Yeah. Thanks, Richard Hugh. I don't know if you're here, but yeah, thank you for this. I like I like this. I like this. I like your text. Anyway, so I sort of kind of grab this from. All right. So here's a custom text, right? So I mean, like, can you meet for lunch? Right? And then you can do. Here's like a spammy word, right? So let's see how our classifier is doing with this text, right? So again, look at the text. We are simply, right, doing the pipeline to transform text. Remember, because we have to convert the text to vectors, right? So do the transform, my x, and then I say the algorithm dot predict my x. Any other predictions? And look at this again, so right, again, it's kind of, it's kind of doing. I think I got this wrong. Let me see if I can do this again. No. Yeah, there you go, right? So see, okay, it marks this one as a spam. Win instantly gets this one. It misses this one, right? I'm guessing probably these words were not in the original text, right? That's why it's unable to capture that. But yeah, right? You can say, can you meet for lunch? That's clean. Anyway, so you can play around with this one. You can sort of, add your thing. Try to sort of mimic some of the spam keywords here, right? If you look at the data, right? So, right, so you can sort of say, try to say, hey, free entry or something like this, right? So kind of we create a message like this with free and entry and something like this sometime, right? It'll say, this is a spam, because why? Because it has seen those words in the spam email before. So how the algorithm working? The algorithm is basically probability scoring, right? It says, okay, if I see the word win, what are the chances message is spam, right? So what it's doing is it's basically doing, just multiplying all the probability, right? If I see instant, what are the chances being a spam? Probably pretty high, right? If I see medications, right? Yeah, probably it's high chance of being spam. So yeah, it's probability scoring. Because why? Because before it has seen the word medications in like a lot of spam messages. So it will sort of calculate the probability. It's to the reverse problem, right? If I see the word medication, highly likely it's spam. That's what, right? Good, guys. Very good. Very good questions. So that's the end of the lab. Let me do one more thing really quickly here. Give me 1 sec. Okay, sure. That's why I want to verify something. All right, I think we have done everything here. Is there anything else here we need to go over, guys? Right, so, nairbase, so, right, spam data set. And also here, I said, look, I mean, you can choose any other data set as well. And this one, I'm kind of, this is what I'm pushing you to select your own data, pick your own data, plug it in, and then see how well nairbase does, right? Sorry, Chaitanya, I see your message as in plotting, as in you mean the words? Is that what you want to plot? Right. So it's going to be a little tricky, because here's why. Because this is high dimensional data, right? Where's our how many columns we have, right? So right. So imagine you want to try to plot, like this many columns. So not right away, but what you can, there's a technique you can use. It's called PCA, right? We haven't covered it just yet. If you want to plot the data, right? I'll just put this number here, right? Plotting high dimensional data. Look at PCA algorithm, okay? And you'll see some, pretty good examples on the internet, so you can just, kind of quickly feed them in. So what PCA will do is like it'll reduce like these 8,000 dimensions into like 2 dimensions, right? Actually, let me show you guys this. Give me 1 second. This is what I had. All right. So here, so in the word-to-vec algorithm, right? There you go, right? So this is a word-to-vec result. So what I'm doing is, right, remember the word-to-vec algorithm, produces like a high dimensional vector, right? It's like almost like 32 dimension, I believe, right? There you go, right? So how do I visualize the result? What I can do is I sort of reduce the 32 dimensions into say 2 dimensions. And that's what's called PCA, right? Again, that's the algorithm. So once you do this, see, here's what I'm done, right? So here's my word-to-vec. So it's like I reduce 30 dimensions into like, 2 dimension. And you see how the words are mapping. See, here's music, saxophone, and piano, right? Meaning like all the music instruments are kind of, mapping pretty close to each other, right? All the food items, right, chicken and kitchen and, right, they're kind of close together, right? And things like Linux, screen, computer, they are kind of close together, right? So you can see, right? So, I mean, yeah, you can still map this from high dimensional to something we can visualize, right? Yeah, definitely. So look at PCS1, that'll help you. You have to do some work to kind of shape the data to the format PCA expects, but it's pretty straightforward. You can look at the examples. Yeah. And then, yeah, so actually that'll be interesting to see what the map looks like, right? To see, right, how the words cluster together. Good question. Yeah. Let's see. All right, guys. So just taking questions. Again, we're going to wrap it up in a few minutes. Let me look at the questions here. Right. So if we have kind of distinct features, what you want to do is you want to look at trees. Because then you can actually combine the results into one. Those are called ensemble methods. That's what we are going to look at next. Okay. So we will look at these next. Yeah, especially when you want to combine multiple algorithm results, ensemble methods. So guys, any other question on this one? This is pretty good. So please look at the right. You have the links already here, right? So again, Sachin, thank you. Really good notebook, and I also borrowed something from Richard Yu. So thank you both of you guys. All right. That's it. So now you guys can see, right? A simple naive-Bayes algorithm can work with real-world data with a pretty high degrees of accuracy, right? That's not bad at all. For like just maybe 15-20 minutes of work without doing a lot of data manipulation. So that's why naive-Bayes is pretty great, right? Anybody did naive-Bayes on the on any other data? I'm kind of curious. So naive-Bayes does really well on text data, as you guys can see. Has anybody tried it on any other data? Oh, okay. So what kind of data is this? Interesting. Yeah, yeah. I haven't seen the astronaut data. Do you have a link for that, Isray? Yeah, that's pretty cool. Sounds pretty cool. Huh. Do you have a link for this? That sounds pretty cool. The astronaut data. Oh, cool. Okay, COVID data. So okay. So basically, what I would recommend you guys, if you could do me a favor, you guys can share the data either in the Google Groups or Slack, so others can look at it too, right? Because like the part of the reason is, let's look at this one. Okay, very good. So Vasilios, I'll just put the note here. So you did COVID, right? Okay, so I'll just put the note so people can look at this. COVID-19 data. All right, so I hope I got your name right. And yeah, that's one right now, yeah. Cool, guys. Yeah, again, right, so this is why we can share the work with everybody, because you'll be learning from all each other, right? So that's very great. Yep. Again, right, please share your results, guys. Again, I'm featuring some of them, so it doesn't need to be here. You can feel free to share on the Slack window as well. All right, so next week, here's what I'm thinking. We have covered 3 algorithms, right? So next week, what we're going to do, let's cover, so I'm kind of torn between counting KNN. So let's look at KNNs next week. And then what I'm going to do is I'm going to set up a cross-validation contest. So what you want to do is, right, so now we have 4 classifiers, right? So which one do we do, right? Which one can we use? So what you guys are going to do is we're going to do KNN, right? It's a pretty simple algorithm. And you're going to run a cross-validation test to figure out what's the best algorithm, right? So I'm going to give you some data, and you're going to say, you're going to run cross-validation, and this one also, you're going to pick your own data as well, right? And see which of the algorithms give you the best results. So now that we know the algorithm fundamentals, let's start with that. So next week, let's see if we can do KNN, because KNN is usually pretty simple, right? You can see very easily. And then I'll also, so now that you guys are doing classification, it's pretty straightforward. We'll also do cross-validation. So what you can, again, so the idea is clear, right? I'm going to give you data. Let's say, let's say you're doing the COVID-19 data. So you're doing classification. Which algorithm is going to give you best results? So you're going to try them all. You're going to first try them manually, and then we're going to try them with cross-validation. And so this will give you an idea. This is how we'll do in practice, right? We have a short list of algorithms, right? We can do this, right? We can compare them together. So I want to do this before, because once we do the trees, then we'll revisit it again. We'll look at, we'll compare the tree algorithms as well, right? Things like random forest, boost algorithms, things like that. Right. So that kind of makes sense, guys. So we're kind of like a stepping back and comparing everything we learned. Yep. So exactly, right? So that's where the cross-validation comes into picture, because cross-validation can do hyperparameter tuning as well, right? So for example, you are using SVM, and SVM, you can tweak the way some hyperparameter in SVM, right? Cross-validation will actually do this for you, and then figure out the best hyperparameter. Exactly. Yep. Yep. So I kind of want you guys to get used to this too, because this is how you're going to be doing in real world. Because nobody's going to tell you, okay, hey, here's the data, use SVM to classify, right? They're going to tell you, here's the data, build a model, right? Build the best model you can. So how do you find the best model? Like this. All right, guys. So again, we'll kind of do this next week. I'll set up the documents and sort of set up the links and send you guys the homework, right? So give me 2 days or so. Yeah. So is that good, guys? So I think that'll be a good exercise for us to. Right. So and also, actually, some of you asked for break week. I think this might be a good opportunity as well, right? So what we can do is next week and the week after, we can take a break. So we'll kind of have you a chance to catch up with all the classification algorithms, and also going to do some, some project-based assignments as well. Yeah, would that make sense, guys? Can I do like a right next week and this week? The next week and the week after. Yeah, yeah. So let's do that. I think that makes sense. Cool. All right, guys. So give me some time. I'll kind of put all these together, and I'll send out the assignment. So the goal is, right, we are going to do KNN, and this is going to be very straightforward for you guys, because you guys have already done three algorithms. KNN is very straightforward, right? Then what we are going to do is we are going to pick a project. So and that's what you guys are picking your own data, right? And I've seen some pretty good data, so that's very good. And then you're going to use your data. I'm going to give you one data set, diabetes, right? That, and also you're going to choose your own data, and then you're going to try all 4 algorithms. and then come back and say, okay, what's the best algorithm you found? And remember, so there's not going to be like one best algorithm. It's going to be algorithm per data. Like for example, when one data set, SVM will do better. In another data set, maybe naive Bayes will do better, right? But it'll be fun to kind of experiment, right? So let's do that for next 2 weeks, guys. I think that's a good break as well for everybody. Yeah, that sounds good. All right. Anything else, guys? So we are almost at the end of the session. Anything else we should discuss? Exactly. Yeah. So we've been going at a pretty rapid clip. So I think a break week will be good, and also do like a little exercise as well. Yep. Sounds good. All right, guys. I'll send out the emails. Thank you so much. So let's see if you want to meet next week. It's up to you guys. We can either meet or we can meet after 2 weeks. Anyway, I'll put this on the email and people can vote and then figure out. Okay. Thanks, guys. We'll check your email and then we'll plan our next week. Okay. Thank you.